Hello and welcome back to the IB Chemistry May 2025 TZ2 exam walkthrough. This is paper 2 for HL. For question 2, if you're looking for the marks that are in common with SL, as you can see here, they're already filled in. That would be in the videos in this playlist here. I'm not going over that again. So this is going to be just the unique marks for HL only. And so for this one, the first unique HL mark is going to be this 2B3. And so that is going to be the state, the enthalpy term that characterizes the strength of the bonding between the ions in an ionic solid. And so fun fact, actually, I believe, let me look, is that your data booklet actually, yeah, this one does, your data booklet does kind of define this for you, even if you forget, because it tells you that the lattice enthalpy values relate to the endothermic process in which the gaseous ions of a crystal are separated to an infinite distance from each other. And so whenever you're thinking about the strength of an ionic solid, it's literally like, okay, well, how much does it take to tear it apart, right? And so the gaseous ions of a crystal are separated. That is tearing it apart. So it's lattice enthalpy. So fun fact, that is in your data booklet, funnily enough. But it is kind of just a vocabulary thing of knowing the different types of enthalpy. I'm not gonna lie, I'm also not really sure why they put this on HL only, because SO also has to know this just for ionic bonding. Anyways, for this next part, it's going to be this section. God, I don't even know no more Roman numerals anymore. 6, 7, 8, 8. I'm dumb. Anyways, for this part 8 of this 2B, and so it is to discuss the products at the electrodes whenever aqueous thallium sulfate is going to be electrolyzed. And it gives us the standard reduction potential of thallium as being negative 0.34, and then to check section 19 of the data booklet. And so whenever we're thinking about our ions that we have for this aqueous, because it's aqueous, that means that we have H plus as well as OH minus. Okay, H plus would form hydrogen gas. Meanwhile, this OH minus would form oxygen gas. Okay. Meanwhile, from our thallium sulfate is we do have thallium plus, which would just form some thallium metal. And then we also have this, no, go back, sulfate ion, which would form, honestly, question mark. I don't even know what it would form, honestly. And so we were thinking about kind of where each electrode, these processes would happen at, because we kind of have two different things, I'm going to say, like, I imagine like in a boxing ring. That's kind of the visual I'm getting, like, HV, Thallium, oh, who's going to win? But in terms of like what process they're trying to do, is this just, you can think of it like this. H plus and thallium are both cations, so they are going to be attracted to the negative electrode, and so it actually gives that to us. So they're both going to be attracted to the cathode, and so the cathode is, you can think of it like this: is there's red cat and ox. These are the mnemonics that you should recognize. Okay, and so red cat, so they both are going to be undergoing reduction. Okay, and so you're going to look at the reduction potentials. And so we already have that for thallium, it is negative 0.34. We're going to be looking for the one that, because there's a reduction potential, you're going to be looking for the more positive. The more positive reduction potential is the more likely to be reduced. Okay, and so we're going to go over and look for our hydrogen gas one. That's over in the section 19 of the data booklet. We were looking at this earlier. Okay, so we have, for our hydrogen gas, is going to be negative 0.83. Okay, and so because we have thallium here, as it is, let's see, negative 0.34 in comparison, so we'll put that negative 0.34. So like thallium is kind of like here. And so since it is more positive, thallium is going to be more likely to be produced. And so our product at the cathode is going to be thallium, which is more likely to be reduced than water due to higher the reduction potential. Okay, and so that's when you are product at the cathode. Meanwhile, over here with our sulfate versus hydroxide, is if you look at the data booklet, is I realized this when I was going over paper 1A, is that and the Pearson textbook uses this value, and I hallucinating or am I stupid? Okay, because the Pearson textbook refers to this plus 0.17 type value, okay, as well as our 1.23 value is both of those, okay? And I get this plus 1.23, right? Because it is the oxidation of water, okay? Because previously we were looking at the cathode, which was reduction. So now we're going to be looking at the anode, so N-ox, which is going to be oxidation, okay? And so whatever we are working with, so the sulfate ions, SO42 minus, or OH, which is also just water, right? And so we need to have OH or our water over on the product side because these are reduction potentials. So we need the opposite. We need our oxidation potentials essentially. And so this one makes sense because you have oxygen, you have your water here. So the oxidation of oxygen to form oxygen gas. However, for this sulfate one, sulfate is on, this is the reduction potential of sulfate. We don't even have the oxidation potential of sulfate. And in addition, sulfate is, if you calculate the oxidation number, it is plus 6. There's no way you're going to go higher than that. So there's literally no way for sulfate to ever be oxidized. And that is repeated in any question is you're never going to have it being oxidized. But the reason why is I always see a textbook and saying, oh, the oxidation potentials, we don't even have it though. And so I don't know why they always refer to that equation in the textbooks, unless I'm hallucinating. Anyways, rant about that over. But either way, all of that is just to say is that the product at the anode is going to be oxygen gas because water is more likely to be oxidized than sulfate. Okay. And we, what's it called, don't even have the oxidation potential of sulfate to even talk about the E cells with this one. So that one is just enough for that to just say that. And you're kind of like, trust me, bro, essentially, because we don't even have the value. Probably because it is just so low. Anyways, so that would be that one. Okay, and so that brings us now to this one for 2C. And so that is to state the feature of the atomic emission spectrum that may be used to find the ionization energy of that element. If you're forgetting this, you should think about how then this part 2 says to calculate the wavelength that corresponds to the ionization energy of thallium. And so this essentially relates that wavelength of convergence to the ionization energy, because whenever you have your kind of pew, 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 that kind of n equals infinity, the wavelength. Why did I put 8? Why did I draw my infinity vertical? Anyways, there we go. Infinity. So like that wavelength essentially corresponds to the ionization energy. However, rather than wavelength of convergence, they're looking for something slightly different. They were actually looking for, I'm going to be honest, I got this one wrong, limit of convergence. So they're thinking of it more from a calculus standpoint. So they're more focused on the infinity and the convergence compared to the wavelength, if that makes sense. They also accepted a high energy limit. So limit of convergence. Would they have accepted wavelength of convergence? Great question. No idea. Like I said, I'm not an examiner. Please let me one day. Let me do it. Let me do it. But I don't know how lenient they were on this term. But limit of convergence was what they were looking for. Um, I put wavelength of convergence. Would they have accepted it? No idea. And so that brings us to this part 2, where it is to calculate the wavelength that corresponds to the ionization energy of thallium. So this requires us to go over to the data booklet and see that ionization energy. So we're going to go over. Scroll. There. Okay, so we're looking for the first ionization energy. So that's going to be in that corner there. So we're going to go over to thallium. So it's going to be 589, and our units are kilojoules per mole. That's important. Okay, so we're going to write that we got that 589 kilojoules per mole. Okay, and so this is where kind of what we have to do is that we have our energy as being the Planck's constant times the frequency. And so we have the ionization energy, okay? And so we can relate that now to the wavelength through the fact that our frequency is going to be equal to this, because we have the equation that C is equal to frequency times wavelength. So we can rearrange that to be frequency is equal to the speed of light divided by the wavelength. Now I can insert that into the above equation as being our HC divided by our wavelength. And we can therefore rearrange the equation to find our wavelengths. So that would be the wavelength is going to be equal to HC divided by E. Okay, and so you may be tempted to directly put the energy, the ionization energy, in there. However, Planck's constant is in, let me find it. Where's our Planck's constant? There we go. Our Planck's constant is in joules per second. Okay, and also our speed of light, meters, whatever. Okay, and so we need to have our ionization energy in joules. Okay, and so this is where we need to then, I always just remember the fact that we have 1,000 kilojoules in one, wrong way, 1,000 joules in 1 kilojoule. My bad. Kilojoule. And so that allows us to convert. And you may think that you're done, except this is the thing. This is 3 marks. Okay? And so you're like, okay, 1 calculation, 2 calculation. I'm missing something. And you're right, you are. Is that the ionization energy is in, now that we've converted it, joules per mole. We need it to be in joules per photon. Okay? Because of the fact that the wavelength of convergence is of 1 photon. Okay, not 1 mole. Is everything is the ionization, all of that is all of in essentially of just 1 singular photon. Okay, and so how do we convert from moles to photons? Well, moles to any elementary entity is going to be using Avogadro's number. Okay, and so Avogadro's number in this case now can be used of our elementary entities is now photons. Okay, and so we have that there is 6.02 times 10 to the 23rd photons in 1 mole. Okay, and we're dividing by that because we want it to be in joules per photon, and so we need our moles to cancel out. Okay, and so now you can see kilojoules cancels out, not joules. We need our joules, and then our moles cancel out to give us joules per photon. And so if you take that 589, multiply it by 1,000, divide by Avogadro's number, we end up getting 9.78 times 10 to the negative 19th joules per photon. God. And so that is our energy that we can now input into this equation down here. Okay, and so we're going to take our Planck's constant up here. So we have 6.63 times 10 to the negative 34th joules per second. Okay, and then we have our C, which is 3 times 10 to the 8th meters seconds to the negative first. This is one where especially I always encourage you to write out your units. This is also another thing also, is that where you can tell that you need to convert from moles to photons because there is no moles that cancels out in this equation here. So you'd be like, how do I get my moles to leave? That is how you get to your moles to leave. Okay. Anyways, so 9.78 times 10 to negative 19 joules is now in our denominator as our energy. Okay, and so now we have our joules canceling out, our seconds cancel out, leaving us just with meters for our wavelength, which that makes sense. If you enter all that in your calculator, you end up getting that your wavelength is 2.03 times 10 to the negative 7th meters. That on its own would be accepted because it did not specify the units here. However, if you want to be fancy and convert it to nanometers, you would just need to multiply it by 10 to the negative 9, which would get you 203 nanometers. Okay, and so that is that one. Okay, so always remember the step of using Avogadro's number. Whenever you're going from wavelength of convergence to ionization energy, you need to use Avogadro's number. Don't forget it.